Hello, everyone. Hi, how's it going? Um, okay, cool. So let me get some stuff set up. This was a hard one to pull together. Hi, hello. Okay, cool. Um, let's see. Let me throw this on screen real quick. So welcome back. So quick introduction, real quick. So hi, I'm Kev. I'm a coach at Magically Hacking. I use the he, him, his pronouns, and I do a lot of different things. So feel free to talk to me about really anything. Um, and today, we're going to try to do computer architecture into the computer architecture. I kind of realized too late after I pitched this idea already that this actually gets pretty complex in terms of where you start and how much basic knowledge you need to have. So I picked a few things here and there. Actually, a bit of assembly because I think that's easier to teach because it's a language than a whole computer architecture in an hour and a half. So, but yeah, so. I also do have a special guest with me because I needed a computer nerd for this really to geek out with me. So I brought on. I'm gonna actually bring them on stream right now. Are you ready? Question mark. Yep. Okay. Cool. So they can hear you now. Hi. Okay. Cool. Great. So this is my friend. His name is. What do you want to introduce yourself? How about that?
Hi, I'm Nicholas. I'm just a student at UMBC. I use he, him, his pronouns. And like Kevin said, I'm a bit of a computer nerd, so.
Yeah. So I brought on a friend to make this a bit more fun. So yeah, don't delete him in chat, thanks. But I'm gonna drop the check-in link real quick for today's stream. Make sure you actually check in. I do have some basic slides, but Nick will also show us some cool things here and there, as well as a random link he just told me about, and we'll see how far that gets. But let me check a few things. Let's see. So maybe today's stream will be a bit more fun than not. Okay, cool. I know, right? Isn't that so perfect? But yes, okay, cool. So first thing, kind of schedule overview with whatever Nicholas want to slot in between. We're gonna go over some basic of a CPU design, the registers, types of register, a bit of assembly, section of assembly files, and then maybe some basic assembly instructions. But again, this is really not set in stone. We will probably move to a few different things here and there. But yeah, again, welcome to the stream. I will actually now play some background music because I hate talking about music. Hold on. Let me do that. Cool. If it's too loud, let me know. But real quick. So this is a little. Is it really like a? Okay, so I'm so confused about that because I sometimes leave it at 10 and no one says anything. So I am actually really thrown by it's apparently super inconsistent. And this is the default music that comes with Streamlabs, so it's not my fault. But yeah, I'm really quiet, but the music's too loud. I don't know what to tell you. Can you hear me now? Yeah, okay, cool. Okay, great, amazing, wonderful. But yeah, so we're gonna go over basic computer CPU design. So really quick, so the CPU, also known as the central processing unit. Here is a diagram of the components that is inside the CPU. So you have something called the program counter, the arithmetic logic unit, or ALU, and the control unit, as well as register. These are external things outside the CPU, such as your main memory, which is things. No, I did not know that, Adam. But which are things like your actual more permanent long-term storage, such as your hard drives, and so much more. Your input-output systems is just stuff you interact with the computer with. But you can see that a register is generally a really small component within CPU. CPU is already super small. A register is even smaller, and there's a lot of different types of register. So the program counter is what points to the executing instruction with the I can never say this word. I can never say this word.
Arithmetic logic unit?
Yeah, There you go. Thanks for the introduction. Is like the calculator of the essentially central processing unit, and then you have the control unit, and this makes a CPU. Anything you want to add, Nick? I don't know. Help me out.
The ALU is also like if you do like bitwise operations like ands or ors, that also handles that.
And we'll go over what bitwise operations are later.
So like if you have a bunch of bits and you want to like compare them to see like whether this bit is set or this bit is set in like two different numbers, you can do like an OR operation and it will return if either bit is set, or if you do an AND operation, both the bits have to be set for an output of 1. So you can build these like simple things up into like a lot more complex stuff, but at its very base, it's just checking if either one of the two bits are set or if both of them have to be set.
Okay, cool. Okay, so really quick, so what is really important working with anything on a lot more lower level as well as with assembly is understanding the register. So a computer register essentially is the smallest amount of memory within a computer. Within a computer central processing unit, unlike other pieces of memory, it's actually stored within the actual CPU. It's built in. It is used to hold data and instructions temporarily while it's being processed. It's also used to store common, frequently accessed memory as needed. The register are, again, the fastest type of memory available to your computer. And there are generally a couple of different types of registers, such as the general purpose registers, the floating point registers, and program count register, and so on and so forth. The number of registers and their size can vary depending on the specific CPU architecture we're going to be dealing with. We're going to look at x86 assembly later, so we're going to actually deal with the x86 architecture. But that being said, real quickly on a few different types of registers. So for the general purpose registers, you have a few of your common ones, which is EAX. EAX, just think about these as tiny. What about cache? We don't talk about cache here. But no, actually, I don't think, Nick, help me out here.
So
cache? I don't think cache is with the actual.
Cache is like kind of a more complex thing. So in a simple processor, we're not really gonna hit on that too much. But yeah, it does make your operations a lot faster. I'm trying to remember. It might be
Because I don't. Is it?
Yeah, we'll get back to that. Maybe I'll have an answer for you.
No. So because this is the AI month, I have ChatGPT pulled up right next to me for exact questions like this. So the answer to this, apparently, according to ChatGPT, is a cache is a small, fast memory that is used to store frequently accessed data and instructions. The purpose of the cache is to improve performance of a computer system by reducing the time it takes to access data from a slow memory, such as the hard drive disk or the main memory. I think maybe the cache memory is actually what the register sits on. Maybe, but I have double check on that.
Yeah, I just looked and it does say it's on the CPU directly. So if you're doing a lot of like common operations, like you said, the CPU is really close to like the cache, so it's really quick memory.
Okay, cool. That is okay. Hello. Hello. Can you hear me?
Hi.
Okay, cool. Oh yeah. Okay, so that's your answer for now. But yeah. Okay, so we're gonna have a few of these registers, so you can think of each. So you can think there's multiple register within a computer. Actually, I should have taken a picture. Give me 1 second. I'll get a picture. So you can think of. See, this is the great thing. Hello, hi. Make sure to check in. And then if you're checked in, if you have any questions, feel free to ask. But actually, I am going to stop sharing my screen temporarily. Reshare my screen. Give me 1 second. Okay. Actually, wait. Actually, no, this works. So I am going to grab a picture real quick so people actually can kind of visualize what this looks like. Open image editor. Cool. Cool. There we go. We're going to build this up a bit. Okay. Okay, so really quick, cool. So a computer will have many registers serving different purposes. You don't have to worry about it saying R. That is just defining the different ciphers. So you essentially just remember it's AX, BX, CX, but you can look at the font, some of them are EAX or RAX, depending on what type of architecture you're looking at. But essentially, it has a lot of general purpose register. It has a lot of floating point registers. It has huge register in some. It's different per different type of architecture you're dealing with. But you can think of it as each register serves a specific purpose, and we're going to go over each one. So later when we do assembly, you would understand why each register and what to use them for. I can make the screen a bit bigger. Can you see it now? If not, let me see if I can make it bigger. Give me 1 second. Cool. Can you see the screen? If not, we can try this mode, but it's not by that much bigger generally. But yeah, so going over that, so real quick, we're going to go over real quick a few different type of registers. So you have EAX, which are generally used to store your return value. So it's like when you're programming in a regular language, when you, instead of just being able to hit return something, you want to store your return value into EAX for any other purpose. So each of the general purpose register you can really use for anything. But the EAX is also where you would store the return value if you go into a function call within assembly or yeah. Then you also have EBX, which is generally a regular register. You can use that pretty safely. No, nothing else really depends on it. You have the ECX, which is the loop counter. You have the EDX, which is used with EAX when you do multiplication and division. We're going to go over that a bit later. Again, I realize that computer architecture is a lot harder of something to teach, especially for beginners. But yeah, that's still fine. And then we have a few other general purpose registers that are pretty useful. So if you get later into computer science, you would know that what essentially a stack is. So with these kind of deal with that. So first thing is you have the ESI, which is the source pointer. It points to the source of what you're operating with. The EDI, which is the destination pointer, it points to what destination you're operating with. So you have your source and destination. Then you have ESP, which is a stack pointer, which point to where you're currently at in the stack. And then you have the EBP, which is the base pointer, which points to where the base of the stack actually is. But yeah, Nick, feel free to interrupt whenever.
Just kind of like, yeah, some of the registers you really don't want to change, like the stack pointer and the base pointer, because the computer itself is like using those to keep track of where it can store things. So you can really mess up some programs. So just stick to like certain registers because some are really important.
Yeah. So essentially, when you're doing your daily things, if you're working with assembly, you really want to stick to the first row of register. So EAX, EBX, ECX, and EDX. Unless you really need to and know what you're doing, you can actually cause different type of chunks or skip over things in the stack. But unless you really want to be doing that, you don't really want to touch the general purpose register list on the second row. But yeah. With that aside, we also have the EIP, which is the instruction pointer. It points to the current instruction that we're operating. We're not operating, that we are currently conducting. We also have the EFlags, which is essentially status register that tells us when you're doing operation. You'll see that it's not like, oh, math doesn't work the way you think math works. I mean, math does work the way you think math works. It just doesn't look like that. Okay, I don't know how to explain it without doing it, but essentially, division doesn't work how you think division works, or it's really boils down to a lot more simpler whatever I can't say that word, arithmetic does. Yeah, thanks. To determine if you, let's say, want to jump or not, where something is true or false, it boils down to really simple arithmetic done by the ALU. And so you need things such as the zero flag, which you could tell. I forgot, what does zero flag tell you?
So
something's positive or negative.
Will be, if you do like an operation, like subtract this number from this number, if the result is 0, then the 0 flag is set. So if we want to check if two numbers are equal, we can just like subtract them. And then if the result's 0, then the numbers are the same. So
yeah, you see, so you just lose your cool comparison operator. So you use use the flags.
yeah.
Hold on, what is carry flag, Nick? You wanna give us a quick spiel?
So it's been a sec since I did this, but carry flag is if we have if you're adding two numbers and sometimes like if you're adding 9 plus 2, it would be like 11, but 11 doesn't fit into the ones place, so we have to like carry the 1 over. So if we do a calculation and it has a carry at the end, then the carry flag would be set.
Okay, cool.
Like,
And then, yeah,
yeah.
no. So the carry flag essentially is a single bit in the processor that indicates the result of the arithmetic operation, and the carry flag is set when, well, let me see, when it used, let's see, let me double check this. It says the carry flag is often used in conjunction with other flags such as the overflow flag or the zero flag to determine the arithmetic operation and control flow of a program. For example, the program can use carry flag to check if an addition operation has resulted in a carry to handle overflow property. So essentially, it's when you do math, when you do math with registers and the number is too big to fit in a register, it tells the computer that you might need to look at a different register or continue because it's too big to fit in one register. But yeah, so as with that, what is assembly real quick? So this is where we're getting at because I think this is a lot easier to teach than actual computer architecture. So assembly is a low-level programming language. It is the computers. It's to use to program computers at the machine level, and it's a series instruction that can be executed directly by the computer CPU. It generally uses I can't say that word, code. You want to try give it a shot, Nick? I can't say that word.
Oh, mnemonic codes and symbolic
Yes.
addresses.
Yeah, there you go. To represent individual instructions. So instead of being able to write such thing as like enter blah blah blah, or like write things like for I in a range, etc., you would have to use pretty simple mnemonic codes and symbolic addresses to represent each individual instruction. And it takes a lot more lines of assembly to do the same thing you would need to do in a higher level language. So example of that, as you can see, to write a string to standard out, you would first have, we're going to go over what each of one of these do later, but essentially you have to write each thing. So what this line does is it moves 4 into a register. We talked about EAX earlier, so it will store 4 there. It moves 1 into another register, which is EDX, which we talked about earlier. It moves the message, which we'll actually go over what section.data and text is. But essentially it moves something called message, you can think of as a variable, into the register ECX, and then moves 13 into EDX, and then actually it does int 0x80. Actually, is this an 86? I actually did not check if that's 86.
Yeah, so this is, I believe, like 32-bit assembly. So it's the same thing as like if you know 64-bit assembly, a syscall. Int is just like interrupt, and then the code 80.
There you go.
So.
Yeah, this is why you keep Nick around. It's great. Okay, cool. And then exiting the program, essentially you can see that takes so much more lines to code than if you were coding directly into a high-level language. You can just do standard out and then pop in your things. The where am I blanking? The parameters. English is great. I love it. Into standard out. But yeah, so that's something. So sections of assembly language. I didn't get to change the slide. That's okay. We're going to go over exploring assembly file later, but okay, so you think you couldn't get your Xilinx to work. I'm going to see if I can get my Xilinx to work. There's absolutely no promises. Let's see. Xilinx. If I even have that installed on it. I have a folder called Xilinx. That's promising. Now I just look for an application called Xilinx. Actually, I don't think I have Xilinx installed. So essentially, Xilinx is a modeling program that allows you to model out on a logic level of components. So such as how to build ALU. And essentially what all those tinier components is, right? It just deals with a lot of bits and how they handle bits. So essentially ones and zeros is why we something calls computer just communicating with a bunch of ones and zeros, because that's at the fundamental level. That's what it is. And then if you go even fundamental level, ones and zeros are legit just electric flows and highs and downs of and just get super macro and micro. Macro is opposite. Micro, it gets super micro, and then we're not gonna do that. But yeah, actually, you wanna what is Nick? You wanna show us the thing, the NAND game? I have no clue what that is.
Yeah.
So
I was gonna look at. Okay, I tried to upload a schematic, but
did you?
yeah. So yes, I will get the NAND game. So there's actually this really cool website. It's I guess
You can share your screen, by the way.
Yeah. I give you the
I'll throw your screen
real quick. And okay. Thanks. Okay, so it's this website called nandgame.com, and pretty much you can. It has all these different levels, so it goes from like really basic stuff like making some of the logic gates, and then each level, like the next level, you kind of use something that you made in the previous level to make something a little more complex. And then if you see at the very end, we have like processor making like instructions and control units, and like eventually you get to like a simple full computer, but it's still like the same principles. So this level, we're trying to make an AND gate. So it's like I said earlier, an AND is when both the inputs are 1, then our output will be a 1. But if we have like a 0 and a 1, our output would be a 0. Or if we have both zeros, then it's still a 0. So
freeze real quick.
Oh, yeah.
I dropped the link in chat if you want to follow along. But also, long story short, this is before assembly, so we're talking about component level of building your different really micro components of a computer. So AND gates are really core. If you ever go into computer engineering, they do have a lot of AND gates, OR gates, and different type of really tiny components, and then you get slowly bigger and bigger. But yeah, continue. You want to try to do one?
Yeah. So and also one thing to remember is like assembly instructions are pretty much like they use things that are implemented in digital logic. So we have AND instructions in assembly, which like use our AND gates in our actual like physical computer hardware. So if we're trying to make an AND gate, we already have a NAND gate because I skipped a level. And let's see. So NAND is basically it takes it's like the opposite of it does the AND, but then it reverses it. So we could just invert it, and then I think this should be the right answer, but it tells you on the side. These are like the cases that you have to check. So when A is a 0 and B is a 0, we have a 0 for our output, and then when they're both 1, we should have a 1 for our output. So we can hit check solution, this blue button up here, and then it says it's complete, and we can move on to the next one. And Kevin, how do we make an OR gate now?
The OR gate.
Yeah.
And an inverses OR gate. What is okay? So I can't believe you just put me on the spot, but that's okay. No links there. Wait.
Here, we'll think to it.
Which
We'll
failed? Give me a second. Let me put a point and let me paste
Okay.
that. It's been a while since I've done one of these. Okay, cool. So OR gate should be you're using your AND as a base, right? So you're saying a 0. You put the inverse. So if 1 is 0, 0 and 0 should be so you put the inverse into one of the sides, right? No, yes, no.
Let's see. Into one of the sides, and then like that.
Let me think. Hold on. Wait. Let me think.
I think it's getting close. Maybe we need another one like this. And we invert
yeah. This is so much more complex than I remember it. Okay.
it.
Are you sure? This is so complex.
Yeah.
Oh, I know. I get where I see what you're saying because it adds 1, so you takes 1 bit across. Okay, and then you what are you gonna do? End them for the output again? You can't just pass 2 things to the output.
Yeah, it's
You definitely can't pass two things to output, so you have to do something here.
Yeah, we need to make them into one again.
One, yeah.
Let's just try a NAND maybe.
A
I'm also
NAND.
doing this just guessing.
So yes, as a computer person, we just guess. This is perfect.
Yeah, no, it's been a while. Okay, so
Hold on.
it doesn't work.
What is a NAND?
So a NAND is
explain?
it's an AND gate, but it inverts the output. So
Okay.
if we have a 0, 0 input, then it would be 1.
Oh, okay. So what actually
And
might be
so-
really beneficial is if I go for another thing, so people can see the bottom. So the bottom you have your inputs, and the top you have the gates, and you want to get from two inputs over out to one output with using different gates for your results. So currently there's so much zigzag lines going on. So you're passing input A over to inverse, then you're passing into A, then you're passing B directly into B. There you go. Okay, cool. So what's failing is when you have two zeros, you should be getting a false.
Mhm.
How about use not the NAND? Just use the AND. That's probably
an AND instead. Here, we'll trash that. We'll try an AND gate on both of these. And then
so it flips.
yeah, no, it just flips. So let's see.
I should have known that because that's just not a band. Why did I even try that?
All right, we can think through this for a sec. So if we have a 0, 0, we want it to still be a 0. But if we have either a 1 in any position, then we want it to be a 1. So I'm thinking something like would connecting that work?
That's a great question. Anyone in audience and chat knows? You want to give us a hand?
Yeah.
That also works.
Here, let's see.
You don't have to.
I will look at my
You have notes?
previous, yeah, when I did this. So
That would be great.
yeah. Okay, so pretty much. So we need to. We have a NAND over here, and it's like almost correct just with that. And then I think we invert both of these so that so when we invert like A and B, if they're both 0, then it becomes a 1. So the NAND becomes a 0, since a NAND input, if you have two 1s, it's a 0. But if either of them is a 1, then it breaks the NAND, and the NAND becomes a 1 now. And then if both of them are on, the NAND is still a 1. So
okay, so essentially what you did was you did a not and then you did two inverses from the track over. So wait. So another way to do this, you can just remove the NAND, right? And we can put in an and just put feed the and to inverse and then inverse it out.
Yeah, let's try that. So we put.
Dude, you couldn't delete. I'm just kidding.
And on here, and then you said invert it.
It put inverse right before the output, right? It's the same. It should be the same logic.
Yep, because.
There we go. Whoa, look at that. So yeah, that's so cool.
So as you can see, it's not super straightforward. Like you really have to think about how your logic gates will work together. But because it's so low level, you can't really. There's no like functions that you have to use. So as you can see, it's kind of hard.
This is a super fun game you could play on your own.
Yeah.
It's sounds like a
yeah,
blast.
You can try it out. They have a lot of other levels, so I do recommend if you're interested, go look at the website.
So, since Nick played around, let's see. What we're going to do next is go over the sections of assembly file. And we're gonna bring back a dear friend. If this works, that is. Let's see. Oh, I should have prepped for this. Where is my pen? There's my pen. If this should work, hopefully. Technology has failed me many times, but hopefully it won't today. Oh, this kind of works, but it's glitching. So what does that actually mean? I need to do. You wanna pull that back up and do another round? Do another game.
Okay.
As I do this.
Sure, I'll try. I'll struggle through it while you
Try. Do the hardest one. I'm just kidding. Do not do the hardest one.
Yeah, even let's see, share screen.
Share screen.
Yeah.
As Nick does that, I'll fix my stuff.
Okay. So now we need an XOR. So this is just another logic gate. An XOR, we need the output to be 1 when the two inputs are different. So when they're both 0, it's a 0. So that's kind of like an AND gate. When one of them is a 1, then it's a 1, and when both are a 1, then that's a 0. So I'm thinking this final output is kind of like a NAND gate. Not both of those.
Oh, you weren't on stream, so no one could see you.
Oh.
That's pretty funny. Now you're good now. But
Okay.
I should be
Then-
good to almost fix it, but no.
Sorry. So
Thank
here,
you.
I'll restart. So an XOR gate, if there's only a single one between A and B, then it's a 1. But if both the outputs are 0, then we want a 0. And if both the outputs are 1, we also want a 0. So it's called exclusive OR, since you can only have like exclusively 1 bit on at a time. So let's see. It's kind of like this one is kind of like a NAND with A and B. And then also
After this, we'll get to some more lecture on assembly. But isn't this so fun? You can do this on your free time.
Yeah.
Especially if you're taking a computer architecture class or a basic of what is it? You know what the first class is called? It's like principles of
Computer organization.
or computer organization. So if you take any computer architecture or computer organization class, it's a pretty fun tool to play around with. But yeah, you can see you get all the gates, all the drawings. I didn't even know this game existed, so this is pretty cool.
Yeah, I think. Yeah, it's been a while since I did digital logic. There's a trick to work with the like the input output table, but I completely forget it. So Kevin,
It's okay.
okay.
No, I do have the next thing on the agenda, which is we're gonna break down some assembly things. And welcome to my trusty friend, Whiteboard Paint. So this is our whiteboard in the classroom. I cannot spell, so please bear with me as I fail to spell today. I'm gonna drag this canvas so it's a bit bigger. Okay, cool. We have a bigger canvas now. So what we're gonna do is go over the components of an actual assembly program. So the first thing first, so before your actual assembly program or the start assembly program, we have a few things called sections. Oh, that's not what I want. Sections. And so what sections are how we divide the assembly program up for understanding. So we have 3 types of sections. One type of section we call it data. We'll go over what each of these are. The next type of section, we call it BSS. If you ask me what BSS stands for, I have absolutely no clue. I won't be able to tell you, but that exists. And then you have text section. So what this kind of looks like is generally you would have, depending on what type of assembly language you're working with, but you would generally have section dot data, and then you have things underneath it, followed up by section dot BSS with things underneath it, followed up by the last section, which is section dot text with things underneath it. Oh, and people apparently have comments. Let's see. But yeah, I have no clue what it stands for, and no, I do not what it stands for. What does it stand for?
Block starting symbol was what I found.
Oh, that's odd. Okay, but what each section does is the data section is used for declaring or initializing data or constants that you would use throughout your code, and this section should be things that never change. So you can declare various constant, for example, when you're like a file name you want to work with, or for example, the size of an array, etc. You could declare them within data. You can also declare strings you might want to print out in assembly and data, and so on and so forth. So the BSS section is used for declaring actual variables. So this is, I guess, symbols kind of make sense, right? So it's like your normal, when you're writing a program, let's say in Python, you can say like var A, var B, var C. You would make the variables within BSS. This is where you can move data into variables and move out. So they're not registers, but they are kind of like backup where you're allowed to store data into memory in somewhere. Do you know where actually the variables and BSS storage is located at, by chance?
I think BSS is kind of like the heap, or like some.
So is it stored? Is it stored in a register or a cache somewhere, or is it? Do you think does it get stored? Do we know? You can say no. This is.
It's. I mean, all this stuff is just stored in memory. So.
But what is memory? I'm just kidding.
Well, let me.
What is memory?
Memory is a lot of digital logic stuff. Very complex, kind of.
Okay, cool. But yeah, okay, moving on. So the text section of assembly generally is stored for your actual code. So this is where you generally would do some assembly languages you must begin with, let's say, global start or something like that. And this is where you actually put your actual code. And we're going to go over what type of code you can put in here in a second. But yeah, so data is essentially where you store your constant. It's kind of like, normally programming like in Python, and you have good actual program practices. You put all your constant up front. After that, you would put your BSS. You can create all your variable that you want to be able to use throughout the code. But unfortunately, you don't have such thing as localized variables. You would just use registers for that type of stuff in assembly. So you have that. And then the text section is where you actually write your code, which can utilize things you created in the data section or in the BSS, as well as normal operation that is available to you in the x86 architecture is the one we're looking at. But in any assembly, you can just put anything else under the actual .text section. That being said, we're going to cover our next thing, which is we're going to cover over some of our more common assembly operations, and we're going to do it in x86. But a lot of these are so common, and generally you can see them across the different type of assembly languages. The first one is move, where this stands for move, M-O-V. So essentially what this one does is it moves data of any kind. I should probably not use data. I'm going to put value. So value of any kind. It could be from a register. It could be from, you could write it indirectly. It could be from a math. I can't use that word. It could be from math, or it could also be from, let's say, a variable, and you would move it into a register. So real quick thing, how assembly language works is it goes, the first thing you write is your actual instruction. I don't know why I draw a square. I meant to draw a bracket. So first thing you write is your instruction. Then you follow up by generally it's like your arguments, right? So first were your parameters, whatever you want to call it, at different stages of your development of your program. But first thing you would write is this could either be a register or a type of more generally it's a register. So you do a register, and then generally this could be anything where the data source is coming from, where I'm going to put value, right? So for the move instruction, how this one works, this could also be a register, by the way. This is just anything it needs to complete the instruction. So for example, for move, it would look something like this. You would write move. You give it, so how it works is this is the register. It's different per language, but in x86, we're Intel x86. this is the register we are performing the operation on and storing into. So what this is essentially saying is take whatever value you put here and move into this register so we can use it later on for any type of computation we want to do, etc. So first things first is I'm going to, let's say, use a general purpose register we talked about before, which is, let's say, EAX. And what we can do is we can move anything. So, right, so I would say move something into EAX. And what I can do is if I want to write an exact number in, I can write 0. So this would now make EAX equivalent to 0 is what's going to be stored in EAX. I can also move by using another register. So I can say move whatever is in register EBX into EAX. I can also say, let's say, move whatever is in register, not register, whatever math this computes. You can use some languages, not all. I like to use brackets to compute something in here, and that is what will be stored into EAX for whatever register you have here. So for example, I can, on a technicality level, write, let's say, EBX plus ESI, and this will take whatever's in this math computed, go to that memory address, grab the data, and then store it into whatever register this is. Question?
Yeah, and the important part of the brackets is it actually goes to that memory address. So like, if EBX plus ESI is like a pointer to some string, it would actually just take the first character of that string and put it into your register instead of the address of the string.
This is the memory, right? So what this does essentially, it computes the math inside, and then it goes, okay, this memory address is at this location. And then it will go there and take whatever data is in that memory address and put it into this register. And it's like, whoa, cool. But yeah, so that is move. So move essentially allows you to move things with data or values into a register. We're going to skip some other dumb stuff, and we're going to move to the fun stuff of the word I can't say. Math, also known as arithmetic, or whatever you want to say it. I also can't spell it. It's okay. So we have instructions of your basic math, such as add, which if you can't guess means addition. It's kind of cool, right? How this works. I also can't spell addition, so the might say addiction. I don't think it does, but it says addition. And then you can also have subtraction or sub. I should just give up on spelling and just do. Have you seen the professor or a teacher when they don't really want to spell right words? They just go, and then it kind of just like drags off and dribbles.
Yeah.
But yeah, okay. And then you have, this is a really common one, which is inc, which stands for increment. You also have dec, which stands for decrement. And as you can guess, this is what you do math, right? So you can do like 1 plus 1 is equal to 2. If this is subtraction, you can 1 minus 1 is equal to 0. And then increment essentially takes whatever is in the register and increase it, does a plus 1. Decrement takes whatever in the register, does subtract 1. So let's do some example. So how add will look like is the same type of function as move. It will store the result into EAX, whatever the register you put in here. So I'm going to put EAX here, and then you would give it the value. So take whatever this value is and this value is. It'll take this and add to this, and then we'll store the results in this. Correct? I think so. I think if my memory serves me correct.
Yep.
Okay, great, amazing. So how this would actually work is, so what that means is if I wanted to add two numbers together, I would honestly actually have to do is first I will want to use a move. Let's say I'm going to use EAX. I'm going to move, let's say if I want to do 7 plus 8, I would have to move 7 to EAX first. Then I wanted to do a add, and I can do add EAX, and I can do 8. So this will first put 7 EAX, so take EAX, add it to whatever 8 is, and store it back into EAX. And then EAX will have your result, which 7 plus 8 is 145. I'm just kidding. It is just 7 plus 8 is definitely just 15.
15.
Yeah, thanks. I knew that. I did 145 on purpose. You don't have to come at me. But yeah, okay, yeah. So that's 15. And then that kind of works the same way for subtraction. It's the same type of logic for most of the arithmetic math things. Yeah, Math, great. And then you also have increment, decrement, which essentially all you got to do is give it the register you want to increment or decrement. So for example, inc EAX after 15 is already in there, we'll make it 16. Once I do a dec EAX, it will make it 15. So now you have some basic math things. Okay, that's really cool. So what about that? What else can we do, right? There is even more advanced things in math, which we called mul, which stands for multiplication, right? Shockers, I know, so crazy. I've never seen this notation before. Multiplication, whatever, right? And then you have div, stands for division, division, whatever, right? So we just kind of trail off right there. But yeah, so for how multiplication and divisions work, if you think about it, is at first you would give it. Actually, multiplication is let me think. I think you would store, because multiplication is a more complex one because it can surpass the number of bits your register can store. So I forgot. I need to actually double check which two. Do you remember which register multiplication uses?
Not off the top of my head. I think it's
got it. Understood. So the multiplication uses, I think, EAX for your lower 32-bit, and then it uses EDX for your upper 32 bits. So most of the time, your result will end up here. And to use multiplication, all you got to do is first store something. And how multiplication works is it has to be stored in EAX. So whatever you want to multiply has to be stored in EAX, and you would just run multiplication like this. So for example, if I was trying to compute, let's say, a simple one, I can actually do it. Let's say 4 times 0. I'm just kidding. Let's do 4 times 4. So actually, it's math. Actually, no, that can look weird. Let's do 4 times 5, which is definitely 200. I'm just kidding. It's just 20. But how this would work, right? To use multiplication, first, again, you need to store a value into EAX. So one of either 4 or 5 needs to be stored in EAX because multiplication is. I'm thinking commutative, but I don't think that's correct. Is it commutative? Is that what I'm thinking of? Yep. Where 4 times okay, I hate math theory. So it's 5 times 4 and 4 times 5 is equal to the same thing, right? Yep. That's commutative. I should really know that, but that's a different story. So in EAX, you would store one of either 4 or 5 because how mul works is for this to work, I would first do EAX. I would first move, let's say the first number I want to multiply, well, in this case, let's say it's 4, move 4 into EAX. And then for multiplication, all you got to do is using, okay, I can't spell, mul. And then you would pass it the value you want to multiply EAX by. So let's say I want to multiply 5, I would pass it x5. And this will then store the result, again, with your, because this is only 20. It's low enough, so you'll find 20 being stored into EAX. But if it's big enough, you would find, I think, the overflow bit checked. And then you will find that half of this will get stored into EDX, or the upper 32 bits. And you can read them together or do some odd math that I have not figured out to read the whole number full. Because most of the time, you should really be sticking within EX. Because what 32 bits gives you how much numbers? Is it to the power of?
It's 2 to the 32.
Oh, flip it. Okay. Okay, which is? Quick math calculator. Big number. Yes, it's infinity. I'm just kidding. It's not infinity. It's a big number. There we go. Right, big number. So most of the time, you should not need to use the upper bits. But in case you do, you do have it there. Because multiplication can get crazy. And guess what? Division is even more crazy. I actually don't know. I don't know how division works. I could only remember multiplication. Let me think.
I think it's similar with the 2 registers and then 1 argument.
You're probably right. So division is probably similar, but I'm actually gonna take a look. So Nick, Nick computer fact of the day. Throw something out. Random computer fact, because I looked this up.
Okay, computer fact. So since we're talking about computer architecture, there's this thing called VHDL, and I think it's really funny because VHDL stands for the V stands for VHSIC, which is another acronym. So I think that's really silly.
He's told me this before. It's funny.
Yeah, it's a lot of words. The full acronym expanded is very high speed integrated circuit hardware description language, I think. So
Mouthful is that
yeah,
for
definitely.
sure.
So just say VHDL and people will know what you're talking about.
And
Um,
between that little computer fun fact, I've looked up how division works. So division apparently, you move. A division is actually super interesting. You move apparently the divisor into I think EAX. So and then you move. You can again. You don't have to ever memorize all of the how to use every one of these information because they do change per architecture on. You can always do a quick look. So I know I'm using division, and I'm looking at x86. So for x86, you store the divisor in one. You store the call it the dividend. Yes, the dividend. Sure, it's dividend.
Yeah, dividend.
Yeah, sure. Let's go with that. Yeah, okay. So you set the dividend divisor into one of them, and all you run is you run div, and after you store them, and it will take whatever EAX and EDX after which one comes first and just divide. I think it divides EDX by EAX, and then it will store the result into EAX. Follows the top convention where 32 bits of the lower 32 bit will get stored into EAX, the upper 32 bit will get stored into EDX. But yeah, so that was some math, great math. So now we get to our fun and common logical operator instructions, right? So you have things like XOR, you have things like AND, which we did talk about earlier, and we also even tried to build one and failed. And the one we failed the most on was OR. It's great. Okay, so what is XOR? Well, I mean, there's no NAND, at least not. I think there is. I'm just going to not write it out. But you see, NAND is cool too. But yeah, okay. So XOR, what is XOR, Nick? Do you remember?
So XOR is exclusive OR. So if we have one of the inputs set, then it's like a 1. If we have the other input set only, then it's a 1. But if we have both of them set, then we get a 0 because it's exclusive, meaning like we can only have one at a time.
Okay, so what does this mean again?
So it's going to be 0 and then 1, 1, 0. So yeah, when they're both 1, they cancel each other out and you get a 0 as the result.
So essentially, it's exclusive OR. So OR generally 1, 1 will actually true, but it's not exclusive, so it has to be in one of these. Yeah, exclusively OR. You can't have AND because 1, 1 will pass the AND test, so it's outlier. Okay, goodbye. Okay, cool. Let's see. So the good thing about Paint is I can do this. Whoop, boop, delete. It's gone. But yeah, okay, cool. So we figured out how XOR works, and as you could imagine, XOR you would just do the two register you want to XOR together. And what is unique about XOR and EAX and EAX? You remember, Nick?
Yeah. So if we have two of the same bits set, then we get a 0. But EAX is itself, so all of the bits are going to match. So I think it'll 0 everything out, and we clear the register.
Yeah, this is a trip, not a trip. It's a trick. It's not a trip. You don't take a trip down here, but it is a trick to clear your register. It's generally a more preferred trick than just moving, let's say, a 0 in, because I don't remember why, but this is more of a preferred trick to clearing your register. You just would take the register itself and XOR for itself, and this will set the register to completely empty. And then this, and it gets stored in here. So you can actually export two values, and whatever the result gets stored into EAX with the first register you provide. Yeah, and it's kind of just your regular AND. You just give it two values. It'll do the AND, store it. Same thing with OR, right? So it just does your standard thing, give it two things, compute, store it. Yeah, go ahead.
Kevin, I have a question for you. So using one of these logic gates, how can we really quickly check if a number is even or odd? How do you think we might do that?
I hate you.
Okay, well, no, hold on. So think about what binary numbers are, like, and think about the pattern.
Wait. I should know this. I
Yeah.
do know this. I just don't remember this. But what was your question? Let's put it into
So,
words again. Write this down.
let's try and figure out if using one of these three operations, if any number is even or odd.
Can be used to tell even versus odd. Okay, cool. So using one of these operations, which operation you could use to tell if a number is even or odd? Oh. Let me think. So
Yeah.
if I or
So
oh,
first, you might want to think about what all even binary numbers have in common and what all odd binary numbers have in common.
all up, I already have the 0th bit turned on.
Exactly.
I know that.
'cause-
I'm just trying to think of the actual solution to that.
Yeah. So we just need to check if the first bit is set.
I know. I mean, you definitely wouldn't use or and. I'm pretty sure it's X or, right? No. Yes. No.
Well, what if we
Oh, I
and,
guess you could and.
that sounds right to me. If we and so here first, let's explain what we're talking about. If we have a binary number, since it's binary, everything is in powers of 2, except for the 0th bit, which is a power
So,
of 2,
for
but it's
example,
equal to 0.
if we write this right, what number is this, Nick?
That's
How about we just take 1/2 of it? What
Yeah.
number is this, Nick?
that. So it's 5.
Okay. Are you
Because
sure? I'm just kidding. It is 5.
I was pretty sure.
Okay. What
Because-
number is this, Nick?
That is 4.
Okay. What number is this, Nick?
1,
Oh, I did not mean. I meant to do this.
3,
So, what number is this, Nick?
2.
Okay. What number is this, Nick?
Is it going to be 1?
No, it's
zero,
not one. Well,
Yeah,
yeah. Go ahead.
Yeah, that's a good idea. If we write it out like that, we can see the pattern. Every time we increase by 1, the bit on the end actually flips. So it goes 1. Well, if we start at 0, it'd be 0, then 1, then 0, then 1, all the way up. So we have our pattern, and like you said, an AND gate, if we can just check if that 1 bit is set at the very end. A turning machine.
I'm just thinking. That's a whole different class. But no, it was a joke. Don't worry about it. But yeah, okay, cool. Yeah, so there's your basic and or and XOR operator. Gonna come up with a problem. Another problem we can use to solve.
I don't have any off the top of my head.
Me neither.
To wrap
Go
up
ahead.
the previous problem, can you write the assembly instruction that we would use if there are numbers stored in EAX, just so that people can see? So we AND EAX with the number 1 and instead of add.
Oh, that is and. What are you talking about?
Okay, with just 1.
And this will do what?
So that checks if it's even or odd because
How though?
what's 1 in binary? You could just write it 4 bits. So that's our 1 in binary, and then you can write anything else under it. So the number you're ANDing it with is 0. So look at the 2 most right bits, and they have to both be 1 for us to get an output to this. So they're not, so we get a 0. But if we tried a different number, like 5,
Don't worry about this.
what are you doing, Kevin?
I was writing the rest of that program.
Okay. If we tried like 5, which would be 0, 1, 0, 1, then the ones all the way on the right match.
But this wouldn't give you 1 still.
Yeah, so it gives you 1. So it's
But
You're
does it?
checking if the number is odd. Yeah, so yeah, that would give you 1 because the 2 bits on the right are both set to 1 and you're adding them together.
Hold on, wait. Am I tripping? You're saying and only looks at the last 2 bits.
Well, I'm ignoring everything else because everything on our bottom number is a 0. And if we have a 0 ANDed without anything else, it has to be a 0.
Wait. So if I was to do, maybe I am so tripping. I don't recall this. If I was to do this and this, what would be my output?
Just a 1. It's like 0, 0, 0, 1. Because remember, you have to have both numbers be 1. Remember, like lazy evaluation, if you have an and in your program and the first condition is false, it doesn't even need to check the second one because a false and anything can't be true since they both need to be true.
Okay, cool. Any questions or concerns about that from chat?
Hopefully that's making sense, but
that was a fun exercise right there.
Yeah.
For not normal people though. But no, I mean it was great for normal people too.
Oh, sorry.
That was great. No, it was great. I love it. That was good. That was fun. Okay. But yeah, so I did kind of write the next thing. So I wrote test down earlier. Test allows you essentially compare a value and a value. You can give it a register. Well, you have to give it generally a register and then any type of value you want to compare it to. So for example, you could have done the and thing and tested against 0 to actually determine if it is been equal or not. I mean, if it is even or not, and then you can jump from there using another command like jump, which we won't go more into. And now we're going to try to write a simple program with what we learned so far. So what we learned so far, that is in our repertoire, is move, which again allows you to move something to register. We learned and, which is your bitwise and. We learned or, which is your bitwise or. We learned XOR, which is your bitwise XOR. And then you have add. We learned sub. We learn div, we learn mul, and then last but not least, definitely not last and definitely not least. I mean, definitely not last and definitely not least. What was it? Missing 2 here. Oh, increment and decrement. Increment and decrement. So now what we're going to try to do is we are going to try to use only these operators to write a simple math problem, which we will write is we want to first do, here, give me some random numbers, Nick.
7, 2. How many random numbers do you want?
Keep going.
9, 4.
Next number. Okay, that's it. So we're gonna write an assembly program that computes this, and you have to keep in mind, what is it?
Arithmetic?
Order of
operations. Oh, okay.
Order of operations, right?
Yeah,
so we first will want to do this first, and then we can slowly compute this way across. Okay. So first things first. We probably want to start with multiplication. So we know remember how multiplication works. You have to first store the first value multiplied by into EAX, and then you want to use the mul and provide it what you want to multiply EAX with, and that's where it's going to get stored. So first things first, we also learned a really nice, unique technique to clear out a register. So first things first is we're going to do an XOR, and when XOR, let's use EAX with EAX, so we can ensure that this EAX register has been cleared. And so EAX is currently 0. Following that, we will first use mul, which is a W. Apparently, I can't write. MUL. So we're going to first use multiply. But before freeze, I made a mistake already. So for multiplication, you want to first move, whatever you want to multiply into EAX. So let's move 7 into EAX. So now EAX store 7. So if you follow along, if you look at the register's conditions right now, register EAX was 0, was here. And then this is register EAX is now 7, which is here. I wish I could draw better. Let's try that again. And then EAX is equal to 0. EAX is equal to 7. And we will write mul, which is for multiplication. And then we'll multiply EAX by 2, which actually, let me check something. I think I wrote this down earlier, so I don't forget. I think for multiplication, yeah, I'm right. Okay, so you don't write EAX, because it just defaultly references EAX. So you just write what you want to multiply by. The eraser tool comes in handy here. So now we're going to multiply EAX by whatever the value of 2 is, which will be 02, which will then get stored into EAX. So we can draw another triangle. I mean, arrow. It's definitely not a triangle. If this is a triangle, the world will be built on nothing. It will be built on straight lines of pointers. We're going to move that here, and then we're going to now make EAX equivalent to whatever 2 times 7 is, which is 144, which is not actually, it's just 14, I think, right? 2 times 7 is 14. I
Yep.
know that. Okay. I do know that. I promise you.
I believe you.
Definitely knew that. Yeah, okay, cool. And then where's my mouse? Here. Okay, cool. And then we will now move. So now we've done this part. So this has been done. Next, we want to compute the +9, +7, -4, which can be done in any order. So I can really write this anything first. So I'm going to do a minus first, right? So we use subtraction. And subtraction, remember, you just provided the register. So EAX, I want to subtract it by OX4. I'm going to do addition. I'm going to do to add. I'm going to do EAX added by OX7. And then I'm going to do add again, which I can do EAX added by OX9. Which essentially what this will do is subtract 4, which EAX will become 10. This will add 7, which EAX will become 17. Add 9, which EAX will become 26. So the answer to this question, you can get with this assembly code, and the answer will be whatever in EAX, which will be 26. Voila, check. Well, star. Okay, great. So that's a bit about assembly language and registers and some of your basic operation. But yeah. Any questions, concerns? Actually, let me stop by this present, share screen, window, assembly files. We kind of went over some of this. Any questions? If not, Nick, thank you for hanging around. Probably stick around for some questions, close up the stream. I appreciate you joining for today.
Yeah, thanks for having me. I had a great time.
That's great. Thank you. I appreciate it. Okay, bye. Say bye to Nick, chat. Bye.
Bye.
Okay, that was fun having a guest around. So, but outside of that, any questions, concern from the audience that I can address? If not, I hope that was pseudo understanding. So let's wrap up and go over what we've done so far. We looked at assembly. Actually, you can't see that. The questions. We looked at some of assembly language. We also looked at some digital logic and compute some of that. We also built out some basic low-level components and parts. And then we finally went and learned a bit of assembly in x86 assembly, some of the actual operations and operands. And then we have wrote a small program of assembly that can do some basic, some basic math. But yeah, is there any questions or concerns? Any questions, concerns? If not, I do want to say, let's see. Global hack, wait, camera. hacking.io. I hope you had a bit of fun. Actually, learned a bit of anything. Next time, I think I'm gonna avoid maybe doing something as complex as computer architecture. But today, after me, we actually have a lot more going on. Um, we have at 7 p.m. Eastern Standard Time, so in around 45 minutes, we have the No Light event, which is going to be super duper fun. So please do come back for No Light. But with that, I'm going to template end off the stream here. I appreciate everyone. I'm glad you enjoyed it. Again, if you have any questions, feel free to ask around. It's been a while. I mean, I read assembly a lot. It's been a while teaching computer architecture portion of assembly, so it's pretty fun. Again, if you guys enjoyed it, I really do hope so. Maybe next time I'll do a full-fledged assembly stream. But it's hard because teaching assembly, you have to understand a bit of computer architecture. But I'm really glad you love this and had a chance to learn about something. But yeah, outside of that, please do come back at 7 p.m. Eastern Standard Time, which is within around 45 minutes. And we're going to do No Light, which is a great fun event to relax a bit and de-stress. But with that, I wish everyone a good something and get some rest. Take care, everyone.